Welcome to this Chapter 27 video, where I introduce semaphores in an attempt to control access in my producer-consumer to critical sections. Let's go ahead and get going on this. So again, I'm back in my Threads program. I'm going to introduce something called semaphores. Now let me show you the difference between condition variables and semaphores. I'm actually going to do a get log here on my changes that I made for semaphores. Now, the first thing, and this is very important, you need to include the semaphore.h header. This is in addition to the pthread.h header. You still need pthread.h for your thread create and thread join functions, but in order to use semaphores, you need to include semaphore.h. Semaphores are declared using the SEM-T type, which is similar to the pthread mutex and pthread condition. Really, though, the semaphore T replaces all of these particular variables. Really, what a semaphore is it is an integer variable that has self-contained its own mutex and its own condition. So all of these three things are bundled up into one semaphore. So how do we use these semaphores? Well, we basically take everything that we did before, all of this code where we locked a particular thread, checked to see if it was less than 0, waited until it was greater than 0, decremented that particular variable, and then unlocked it. All of that is replaced with semaphore wait. Now semaphore wait waits on this free semaphore. This free semaphore is very much like our free count integer variable. The free semaphore contains an integer value that is incremented or decremented depending on the call. Semaphore wait will decrement it, but semaphore wait will only decrement it if the integer variable is greater than 0. If the integer variable is less than 0, then the semaphore wait function will block. It will block and wait for this particular condition to be signaled. Once semaphore wait has been signaled, then it can go ahead and decrement this particular, the integer variable inside, and then unlock the internal mutex, freeing that up. And you can see the alternate. When we want to increment a particular semaphore, what we want to do is we want to call semaphore post. Semaphore post does all 4 of these particular actions here. It locks the internal mutex. It increments the internal integer variable, unlocks the mutex, and then calls signal on its internal condition variable, meaning that it will try to have any waiting semaphores rescheduled to be run. So if we take a look at our in this particular code, for the consumer is waiting on the items semaphore. That wait will end when the semaphore post is made. So every time we come to an end where we've added an item to the buffer, we tell the semaphore, yes, we've added an item to the buffer, which causes semaphore wait to unblock and read the data. So we control the order that these accesses are in. So really, you can do everything that the semaphore does with an integer variable, a mutex, and a condition variable. But it is so much more simplified by just simply using one semaphore to handle this. Now, I do want to note that, again, our buffer that we have here is not the critical section. Our semaphores are not protecting the critical section from other access. There is no mutual exclusion here. Semaphore wait, if, let's say, since we're using 2 different semaphores, we're using the semaphore for items and the semaphore for freeze. Let's say that both of these semaphores are set to 5. If semaphore wait comes in here, and waits on an item semaphore that's set to 5, it will immediately exit, decrementing it to 4, and be able to read from the buffer. But if semaphore wait is set to 5, then this buffer write will happen at the same time that this buffer read is happening, but in two different locations. Our semaphores do not necessarily guard a critical section, except for the critical section that may be internal to the semaphore. But what the semaphore does is it allows us to control how many, how concurrent a particular thread can be. So we can allow these threads to run concurrently with just a semaphore. But of course, if we run out of free space within our particular buffer, we're going to block until the consumer frees up more space. And the same thing is true with items. Now, an important aspect of semaphores is initialization. Of course, we eliminate all of the mutex and condition and integer variable initializations to a single semaphore init for each semaphore. Now, there are 3 parameters to the semaphore init. You have your semaphore that you're initializing. You have a 0 value. This should always be 0 when you're dealing with semaphores in threads. You should only ever change this to something other than 0 if you're using semaphores between processes. There's a big difference with semaphores between threads versus processes. If you need to know more, check the man pages. They'll tell you what you need to know. But the third value is what we're initializing the integer variable within the semaphore to. For our items semaphore, we're actually initializing it to 0 because there are 0 items in our buffer. In our free semaphore, we're initializing it to buffer max because there are that many elements available in the buffer, and so free needs to know that. And nothing else changes. We simply do the same pthread create and pthread join to make it work. So if we take a look at our code now, you'll see that it is extraordinarily simplified. Our for loop, which is counting 100,000 times, performs a semaphore wait on free, saves a value in that free spot, calls post on semaphore items to indicate that an item has been added, and then increments its circular buffer index. That's it. The consumer is equally simple. It goes ahead and performs a wait on items. When an item is available, it reads that item off the buffer and produces an error if it doesn't match what it expects, and posts to the free semaphore, letting the producer add items if necessary, and then increments its own internal circular index. Timing code, and then our main code just simply has 2 semaphore inits, 2 pthread creates, and 2 pthread joins. So let's see this run. I'm going to go ahead and run thread, and that came back in 100 milliseconds. 100 milliseconds, 80 milliseconds, 113. This is not 500 milliseconds, it's 50 milliseconds. So very, very fast. 120, 150, 110, 65. So in the long run, what I said here was it ran on average about 100 milliseconds. We actually have an improvement over the original mutex timing, and definitely a much better timing improvement over our condition variable. So in the long run, when it comes to producer consumer, using semaphores is probably the best way, most performant, and frankly the easiest to code method of allowing this to work. So if you're going to use any locking mechanisms for the producer-consumer model, I highly recommend semaphores. This brings me to the end of this Chapter 27 video where I discuss locking the producer-consumer model with semaphores.